Bien, bonjour à tous, bienvenue au séminaire de l'IAP. Aujourd'hui, nous avons le plaisir de recevoir Vincent Vennin, bien connu dans ses murs puisqu'il a fait sa thèse à l'IAP. Et après un postdoc en Angleterre, à Portsmouth, il est maintenant chercheur chargé de recherche au CNRS à l'APC. Alors Vincent est un expert de l'univers primordial, en particulier de l'inflation. Et il s'est aussi intéressé à la création des trous noirs primordiaux, sujet en vogue s'il en est. Et c'est ce dont il va nous parler aujourd'hui, donc je lui laisse la parole. Je ne sais pas si ce sera en français ou en anglais. En anglais. Okay.
Donc, merci beaucoup. Thank you very much. It's a great pleasure for me to be here. I think I was telling Sandrine that I think the last time I talked in this room was for my PhD defense 5 years ago. So it's nice to be back and to talk in a more relaxed atmosphere than 5 years ago. So what I'm going to tell you about is cosmic inflation, which is the topic of my research. But I will also mention another topic, which is maybe of slightly broader interest for the IAP community, which is primordial black holes. So what I will do is spend some time at the beginning setting the background and introducing inflation, the reason why we believe it took place, and what it tells us about cosmology. And then I will explain that under some conditions, large density fluctuations can be produced during inflation that can later collapse into the form of primordial black holes. And what I will try to convince you is that if such a thing happens, there are some quantum corrections that need to be taken into account when describing the dynamics of inflation. And when you do that, you obtain dramatic changes in the predictions you make for the abundance of these black holes. So this is an effect that needs to be taken into account. And I will show some results about that and discuss some consequences as well. So to begin with inflation, inflation is a phase of accelerated expansion that took place in the early universe. By accelerated expansion, we mean that not only the time derivative of the scale factor is positive, so the universe is expanding, but the double time derivative is also positive, so the rate at which it increases itself increases. And it is something which takes place in the very, very early universe, so even before the last scattering surface, at energy scales that are typically very high. So we do not really know what is the energy scale of inflation. We can only put bounds on it. We know that it has to be larger than the scale of the Big Bang nucleosynthesis, so 10 MeV, but it could be as large as 10 to the 16 GeV, so only a few orders of magnitude below the Planck scale, which means that this is probably one of the most violent phenomena that exist in nature, and it also means that it gives access to scales which are way beyond what you can do in particle physics experiments nowadays. So this is many orders of magnitude above the LHC. So when you probe the physics of inflation, you learn something about how nature behaves at those very, very, very high scales. Inflation was originally proposed in the early 80s to solve some of the hot Big Bang model problems, such as the horizon problem. So the fact that in the standard Big Bang scenario, if you look at the fraction of the last scattering surface that we observe with the cosmic microwave background, for instance, this fraction is made of a very large number of causally disconnected regions, which means that there is no causal mechanism we can imagine that would set the temperature in all these patches at the same value. One would have to put the temperature by hand to the exact same value in hundreds of thousands of patches. But if you assume that inflation took place, then you can bring all of this inside the same causally connected patch. And this is the horizon. This is how inflation solves the horizon problem. But of course, an important question is how do we implement such a phase of inflation? How do we realize this A double dot positive? So the reason why it's not so obvious is the following. One can consider the case of a universe filled with a perfect fluid, homogeneous perfect fluid with an energy density rho and a pressure P. And if you write down the Einstein equations for this system, you obtain two equations. The first one, which is known as the Friedmann equation, which relates the Hubble parameter squared. So I think I didn't give the formula, but H is defined as being the time derivative of the scale factor divided by itself. So h squared is given by the energy density divided by the Planck mass. And then you have a continuity equation for rho dot in terms of rho and p. And if you use these two equations, you can obtain an equation for a double dot. And what you find is that a double dot is proportional to minus rho plus 3p. So if you have a perfect fluid with a positive energy density, because of the minus sign, it means that if you want to have a double dot positive, you need a negative pressure. So the fluids that we are used to in the standard Big Bang model, pressureless fluids or radiation fluids, they cannot, because they don't have a negative pressure, they cannot drive a phase of inflation. On the other hand, because we know that inflation takes place at very high energy, we know that we should describe matter, maybe not with fluids, but with fields. And the simplest field that you can think of, which is compatible with the symmetries as well, is just a scalar field. So you can consider just a single scalar field with a usual standard kinetic term and some potential V of phi. Here I have just drawn some potential. And then if you write down the Einstein equations for this field, you obtain that they are similar to the ones of a perfect fluid if the energy density is given by the sum of the kinetic and the potential energy, and the pressure is given by the difference between these two energies. And so if you want to realize the condition that rho plus 3p is negative in such a way that a double dot is positive, plugging these two formulas, you obtain that the potential energy should be larger than the kinetic energy, than 2 times the kinetic energy. So what it means is that in order to realize inflation with a scalar field, you need to find a scalar field which has a potential for which the kinetic energy is sufficiently small, which means that basically the potential is sufficiently flat. If the potential is sufficiently flat, the field slowly rolls down the potential in such a way that its kinetic energy is small enough. This condition is realized, so rho plus 3p is negative, and you have inflation. So, of course, in practice, we don't exactly know what is the potential for inflation, because it happens at so high energy scales that there are many ways to extend the standard model of particle physics and different constructions that give you scalar fields and potentials for inflation. But another interesting property of inflation is that it actually makes predictions, and it makes predictions for the cosmological structures that we see in the universe. And the way it works is the following. So here I have drawn a very simple space-time sketch. So here you have time, cosmic time, t, and physical distances. And here I'm considering a simple model of inflation where the scale factor grows exponentially with time. So in such a space-time, so the lines here are just lines of co-moving, rest observers. So these are just exponential lines. And in such a universe, you have a typical time scale that you can associate. For instance, you can look at these two lines and wait for how much time it takes to double the distance. It will give you a typical distance, a typical time, sorry, and if you multiply it by speed of light, it gives you a typical distance, which we call the Hubble radius. And this typical distance is such that physics happening inside this radius does not see the expansion of space, but physics happening on scales larger than this Hubble radius feels the expansion of space. So I told you before that inflation is realized, we think, with a scalar field. So you can take this scalar field on top of this background and make some Fourier expansion. So you have different wavelengths for each mode. And you can look at what is the fate of these wavelengths. And because of the expansion, what is happening is the following. So at early time, the wavelength of any mode is going to be smaller than the Hubble radius. And this is very important because it means that initially you can ignore or almost ignore the effect of the expansion. So you can set initial conditions in a situation which is exactly the same as just flat spacetime, Minkowski spacetime. And in such a situation, we know how to define a vacuum. We know how to have prescriptions for initial condition. And this is a very important property of inflation, which is to bring all the wavelengths of interest inside the Hubble radius initially, so we can start the physics in a regime that we understand well. And then inflation proceeds, so the wavelength increases. At some point, it crosses out the Hubble radius, and then it starts to feel the expansion. So what happens when it feels the expansion is that you have a quantum field on a curved background. And so you have a mechanism which is called particle production in quantum mechanics. And what it means for us is that the vacuum quantum fluctuations that are contained in the field, they will be amplified and they will produce cosmological perturbations. So at the end of inflation, the accelerated expansion stops, and you have a number of events. The first thing which happens is that the energy which was contained in the inflaton, so the field that drives inflation, decays into the other fields. For instance, the other fields of particle physics, the one that we know, which thermalize and starts and then the radiation era starts. So this epoch, we call it the reheating epoch. And then at some point, the universe becomes transparent. This is when the light of the cosmic microwave background is emitted. And because it's the earliest information we can obtain in the universe, this is a crucial observable to constrain inflation because it's the one which is the closest. And this allows us to give constraint on some of the details of the processes that took place during inflation. So I don't think I need to recall at IAP that this was mapped with an exquisite level of accuracy by the Planck satellite mission. This is a map of the cosmic microwave background for the temperature fluctuation. So the average temperature has been removed. Here you only have the fluctuation, which you see has units of order the hundreds of micro Ks. This is the map by Planck, but just to give you an idea of how well the accuracy has improved, this is the map that we had in the 90s with Kobe. This is WMAP in the 2000s, and this is Planck 2013. So of course it has been updated since, but the situation is very similar. Then these cosmological perturbations evolve under the action of gravity, and they also form structures that we see in the universe. So any experiment mapping these large-scale structures will also give information about inflation. So you can really constrain inflation with a variety of different cosmological observables, even though the CMB is maybe the preferred one because it's a little bit cleaner. So during inflation, quantum vacuum fluctuations are stretched to cosmological distances, and this seeds the large-scale structure of the universe. So this is, again, a sketch just to summarize what happens. The Hubble radius is a constant, so the wavelength of any mode crosses out the Hubble radius during inflation. At early time, you are in a situation where space-time is effectively flat, so you can set vacuum initial conditions, and then on super Hubble scales, you have this particle production mechanism that gives you the CMB anisotropies and later the large-scale structure of the universe. Of course, this mechanism is quite non-trivial because it relies on applying the quantum mechanics on cosmological scales, so it has a number of fundamental implications. But it is important to stress that this is the way that we interpret cosmological inhomogeneities nowadays. We think that they all come from these vacuum quantum fluctuations, amplified by the expansion during inflation. Okay, so now let me move on to primordial black holes and try to motivate why it is interesting to consider primordial black holes for inflation. So this is a possible potential. We don't know exactly what the potential for inflation is, like I said. What we know is that it probably contains a part which is of the plateau type, so which has this form here, but the rest of the potential is rather unconstrained. So here I've just drawn the potential like that. When the field rolls down the potential, one can keep track of the potential energy, kinetic energy, and when the kinetic energy grows, at some point, inflation stops because the condition A double dot positive is not realized anymore. So there is a point at which inflation ends. And what the cosmic microwave background allows us to constrain is the scales. So the scales of the CMB, they exit the Hubble radius at a certain time, and this is the time that we can really constrain with the CMB. So time is usually measured in terms of number of E-folds, n, which is just the log of the scale factor. So between the CMB scales and the end of inflation, you typically have 50 E-folds, but the region which is really probed by the CMB has a length of only 7 E-folds. And there are huge differences between the length scales that concern CMB, which are typically of the at the level of the megaparsec, and the end of inflation where the wavelengths could be as small as 1 meter. So here, if the energy density of inflation is 10 to the 16 GeV, you find 1 meter, otherwise it can be larger. Here, this parameter, RRAD, is just a parameter which has to do with the reheating epoch, so you can take it to be 1 if you want. So you see that there are many, many orders of magnitude between these two scales, and we don't really constrain the potential for inflation between these 2 points. But in fact, something could happen, which is that close to the end of inflation, there is a region in the potential which is sufficiently flat such that large quantum fluctuations are produced and that these fluctuations form primordial black holes later. So it could happen before the end of inflation. It could also happen after the end of inflation when the field, for instance, oscillates at the bottom of its potential. It is another possibility that I will not discuss here. But if it happens either before or after, it will give the constraints we have on primordial black holes, they will give constraints on these regions of the potential that otherwise cannot be probed with the CMB. So primordial black holes have been proposed a very long time ago as being a possible object that exists in the universe that would form at very early time. So the idea is that you form large quantum fluctuations that grow super Hubble during inflation, and later, when they re-enter the Hubble radius, if they are large enough, they can collapse and form black holes. And there are a number of constraints on the abundance of these black holes. So here you have a summary of the different constraints that exist. This is in terms of the mass of the black hole in solar mass, and this is in terms of the fraction of the black holes that contain dark matter. So you have several constraints. Most of them come from microlensing, so the fact that the black holes are expected to microlens astrophysical objects, so if we don't see this microlensing signal, we can exclude. There are other types of constraints. From the plot, you might be given the impression that it is now excluded that PBH form the entire dark matter. But in fact, it's not exactly so for two reasons. The first one is that some of these constraints are debated, to say the least, and should not maybe be here. And the other reason is that because they are subject to astrophysical uncertainties and parameters that we don't really know what value they have and so on. And the other reason is that these constraints are always shown for a distribution of black holes which has a single mass, what we call monochromatic distribution. So we assume all the black holes form at a single mass, and then we constrain. But of course, in practice, we expect black holes to form with a certain mass distribution, which has a certain width. And in fact, people have shown that even if you take seriously all of these constraints, it's not difficult to make all dark matter in the form of primordial black holes, just with a certain mass, a little bit broader mass distribution that would pass all of these constraints. So this is an interesting possibility. One of the reasons why primordial black holes have also become a bit more popular recently is the detection of the gravitational waves emitted by mergers of black holes by the LIGO-Virgo collaboration. Here you have a picture of the different systems that LIGO-Virgo has detected in terms of the mass of the object. So the blue ones are the black hole mergers. And it has been proposed that the progenitors of these mergers, so the black holes that we see which merge, could be primordial. So it's also a possibility that is being studied. And finally, there are some arguments that I'm not going to review, but which are also in favor of primordial black holes that could solve a number of problems or tensions in different areas of cosmology and astrophysics. Here I've just given the link to a nice review of them. So it's not, the status of primordial black holes is not entirely set, but it is an interesting possibility for cosmology that could furthermore provide constraints on inflation. So now let me explain how we compute the abundance of these black holes that we expect form during inflation. I'm just going back to this plot that I've shown before, in which, remember, you have the wavelengths of quantum fields. They initially start in the vacuum, and then they get amplified on super Hubble scales. So what this plot is telling you is that if you are interested in the physics at super Hubble scales, so the physics of the background of the universe on large distances, in fact, the dynamics of the universe on large distances is corrected by quantum fluctuations as they cross out the Hubble radius. Just because if you have a certain mode which is sub-Hubble, it will become super-Hubble at some point, so it will add up to the dynamics of the super-Hubble system. So quantum fluctuations source the background. This effect is typically very small. At the time when the scales that we see in the cosmic microwave background are produced, this effect is very small, but maybe not when primordial black holes are produced. And this is the thing that we need to take into account. So the way that we do it is the following. If we take, for instance, the inflaton field, so phi, we Fourier expand it. So you see, I've put a hat here to stress that it is a quantum field, so it's Fourier expanded, but in the Fourier expansion you have these A and A dagger quantity, which are annihilation and creation operators. It does not really matter, but just to stress the quantum nature of the field. And what I'm going to do is to select in this integral to keep only modes which are wavelengths which are sufficiently large. So Ks which are sufficiently small, the Ks which are outside the Hubble radius. So I look at my field, but I only look at the dynamics of the field on super-Hubble scales. And the idea is to study the dynamics of this object that we call the coarse-grained field. And schematically, what happens is the following. So if you time differentiate this coarse-grained field, typically you have two quantities which depend on time. In this expression, you have the phi k, the usual phi k, but you also have the lower bound of this integral. So when you time differentiate this object, you have the usual classical contribution to my equation of motion. So this is the thing that we usually have. Here I work in the Stroll approximation, which allows me to have a first-order differential equation for phi. It does not matter because one could do it without this approximation, but just for the sake of clarity. And then you have to time differentiate this lower bound, and this will give another contribution. And this other contribution stands for the modes that cross the Hubble radius and that source this coarse-grained field. So because at every time you have new modes in your coarse-grained field, it means that the dynamics of the coarse-grained field is shifted by these quantum fluctuations. And this is what this second term is mimicking. So because, of course, because these are quantum fluctuations, you cannot predict exactly what value they have. It's like a random process. So this term here is a stochastic term. Psi here is a stochastic noise. V is the potential and H is the Hubble radius. So this is in fact a stochastic equation. For this reason, we call this formalism the stochastic inflation formalism, and this is something that has been proposed by Starobinsky in 1986. Now, something you can do quickly is to estimate how important is that new term. And what you can show is that over one e-fold, if you take the ratio between this new term over the classical one, it's typically of order of the curvature fluctuation. So this we can just remember for 1 second. And then you can ask the question, under what condition do I form a black hole? And typically what happens, so as I said earlier, that when the density perturbations re-enter the Hubble radius after inflation, they have a density contrast. And this density contrast is typically given by the curvature fluctuation. So it's typically given by the ratio between this new term, this new quantum noise, and the classical drift. And there is a threshold above which this overdensity will collapse into a primordial black hole. So if zeta is larger than some threshold value, it will collapse into the form of a black hole. So we don't know exactly what the threshold value is. There are some debates, but for us it does not really matter because, as I will show, the results do not depend on the precise value that I take here. So the only thing which matters here is that it's something which is typically of order 1. So what it means is that if I want to have primordial black holes, I need to have substantial curvature fluctuation, but that tells me that the effect of stochastic diffusion is going to be important. So if you want to correctly estimate the abundance of black holes, the stochastic term needs to be taken into account, and as you will see, it can entirely change the predictions. So the way, what you have to do is the following. You have to be able to compute the probability distribution of the curvature fluctuation coming from inflation. So here I've just drawn a Gaussian distribution because we know it should be almost Gaussian, but and then you look at the threshold value, you integrate the PDF above the threshold, and this defines what we call the mass fraction. And this is the object on which we have observational constraints. So here I've quoted this number for the constraint 10 to the minus 8. In fact, the precise value of beta depends on the mass. It can be smaller than that. But as you will also see later, the result almost does not depend on the precise constraint we have on beta. So you can just remember 10 to the minus 8 as a typical number, but it can be different. OK, so the question is, how do we compute this density, this PDF? We have, on one hand, a stochastic equation that models the dynamics of the universe on large distances. And we have, on the other end, a distribution function of curvature fluctuation. How do we go from one to the other? And the way you can do that is using something which is called the stochastic delta range formalism, and which works as follows. So first, there is a result that is known since some time already, which people call the delta range formalism, and which is the following in perturbation theory. So if you start from a hypersurface which is spatially flat, and if you evolve it until a second hypersurface, which has a uniform energy density, then you can show that the curvature fluctuation on this final hypersurface is exactly the same as the fluctuation in time if you measure time with the number of e-folds n. So I go from one point here to one point there, then I have a neighboring point, so I can go from this point to this other point, and the time it takes along these two paths is going to be slightly different because the universe is perturbed. And the fluctuation in the time, if I measure time with the number of e-folds, is exactly coincides with the curvature fluctuation. So this is something that is known. So how does it help? So it helps for the following reason. Because we have a stochastic process, what we can do is, of course, solve for this process. So for instance, we can say that we start from a given value of the field phi. We know at what point inflation ends. We know what is the value of the field at the end of inflation. So we can generate a realization of our stochastic equation, for instance, the red curve. So it's noisy. Of course, here it's the amplitude of the noise is exaggerated, but just for the sake of the example. And then at some point, phi goes below phi n, so we know inflation ends, and the duration of inflation is n1. But of course, if we simulate our stochastic equation again, we will get a different realization, and this different realization will take a different time to terminate inflation, maybe n2. So if we do that again and again and again, we have a large number of times, and if you have a large number of times, we can draw a PDF, a distribution function of these times. So in stochastic inflation, the time is a stochastic quantity, which is given some PDF, which means that because the curvature fluctuation is exactly coincides with this time, it means that the stochastic equation precisely gives you a way to compute the PDF of the curvature fluctuation. So the idea is that you take the stochastic equation that drives the evolution of the field. With that equation, you compute the PDF of the times. It gives access to the PDF of zeta. So you have the PDF of zeta. Then you integrate your PDF between a certain threshold and above, and it gives you the mass fraction. So this is the program that we need to implement. Of course, what is difficult is to compute, what is not a priori easy, is to compute the PDF of these times. But at least numerically, you could imagine that if you simulate your stochastic equation, at least you can do it numerically. But in fact, it turns out you can do it analytically as well, which is what I'm going to show. So this is called the stochastic delta range formalism. It contains many technical aspects that I will skip, but just try to give you some ideas and the main equations that come with it. So the first thing you can do is write an equation for the moment of the number of e-folds. So here, the n to the power n is just the mean value of n to the power 1. So if n equals 1, for instance, it's just the mean value of the number of e-folds. And this quantity depends on the field value at which you start inflation, obviously. So a prime here denotes a derivative with respect to phi. V is just the potential, but rescaled by the Planck mass. And you can obtain this equation which relates the moment of order n to the moment of order n-1. So in fact, something I sometimes like to mention is that I found the ways to derive this equation in a PhD thesis by a French mathematician who is called Louis Bachelier, who was a mathematician in the early 20th century, but who did financial analysis. So sometimes we say that the method that we develop in theoretical physics are then used in finance, but it's in fact an example of the opposite happening. But even though this equation comes from finance, it's still correct. And so we can use it to extract information. So for instance, one thing you can do is solve this equation for small n equals 1. So if small n equals 1 on the right-hand side, you just have this quantity is just 1 because it's n to the power 0, so it's 1. And this becomes an ordinary differential equation for the mean number of e-folds that you can solve analytically. And this is how the solution looks like. So the details of this formula do not really matter. But I would like to stress one thing, which is that you see it involves some integral over the field space between the value of phi at the end of inflation, and in fact, phi uv is just it's where it's a UV cutoff, but you can take it to be infinite if you want, in most cases. So it covers the entire inflationary domain. And this makes sense because you have a stochastic process. So a priori, you are able to diffuse and scatter and probe any region of the potentials, which makes sense that the answer depends on the entire potential. But it's something which is already different with the classical setup because here you really have access to everything in your potential. Of course, this expression looks very much different from the one that people are used to in the classical limit. So how do I recover the classical limit, the limit where I can ignore the stochastic term in my equation? In fact, it turned out that V here, because it's the potential energy in Planck mass, it's a very small number. It typically has to be smaller than 10 to the minus 10. So 1 over V is a very large number. And because you have exponentials of 1 over V, it means that you can do some saddle point expansion. So you can do the saddle point expansion if V is much smaller than 1, but also if this criterion is satisfied. In fact, I will write it down again because it plays some role later. So V squared over V double prime is much smaller than V prime squared. If this is satisfied, then you can do the saddle point expansion, and at leading order, you recover the classical result. So the red expression here is the classical usual result. And you see that this result, contrary to this one, only depends on the shape of the potential between the time where I start and the end of inflation. Okay, it does not depend on the entire potential anymore, which makes sense, because if you don't have any stochastic noise, you just roll down the potential. And what happens to the potential very far away at high energies does not matter. And then you can do it at next to leading order, and you have some first order corrections, so on and so forth. So then when you have this result for the mean number of e-folds, you can plug it back to this equation if you evaluate it for small n equals 2. So if small n equals 2, here you have n minus 1 equals 1, so you can replace the right-hand side with this expression. And then you have a differential equation you can solve for the second moment, for the mean value of n squared. So if you have the 2-point function of n squared, you have the 2-point function of n, you have the 2-point function of zeta. So you have the power spectrum of zeta, and you can find again an expression for the power spectrum of zeta. So the expression starts to be looking a little bit more complicated, but again, the details do not matter. You still have the fact that it depends on the entire field domain. And again, you can do the same saddle point expansion, and at leading order, you recover the standard result, and then you have corrections, so on and so forth. Yes?
Here you meant V squared times V double prime? Divided by V double.
Here? Here?
Here is it divided? Or?
Yes, it's divided, sorry.
Over there it is multiplied, no?
Yes, so I'm wrong somewhere.
Because this goes to 0.
Yeah, sorry. Yes. Yes. Yeah. There is no eraser. Yeah. Okay. Yes. And again, so you could do it again and again. If you have the solution for n squared, you could plug it in your equation and obtain n to the power cube. So then you would have access to the 3-point function of zeta that would give you non-Gaussianity. There is an expression for the F and L parameter, but I don't show it to you because it takes more than a slide. But still, it's fully analytical. You can do a saddle point expansion in that expression again, and at leading order, you recover the standard result, and then you have some corrections, so on and so forth. OK, so this is a way to compute the first moments of your distribution. But the thing is, we don't need only the first moments of the distribution. We need the entire distribution. And the reason is, as I showed before, the PBHs, they form on the tail of the distribution. So if you just have the first moments, what you have is an approximation of the distribution close to the maximum. So you can well resolve the maximum, and with higher and higher accuracy as you go up and up in the solving the equation I showed. But for the tail, it's not going to be a good description. So we need the full PDF. And this can be obtained as follows. So here I wrote again the Langevin equation that drives my inflaton field on large scales, which is a stochastic equation. From this equation, one can derive what is called the Fokker-Planck equation, which is an equation for the distribution function of the field at a certain time. So you start your system somewhere, then you let time evolve, and you have a distribution function of the field value, which obeys this relationship. So it's dp over dn equals some differential operator acting on p, which we call the Fokker-Planck operator. And in fact, the equation that I showed before, this equation for the moments of the number of e-folds, they can be written in a very compact way using this Fokker-Planck operator, just like that. So it's the adjoint Fokker-Planck operator acting on the nth moment equals minus n times the n minus 1 moments. And then you can show that this equation is correct. So this equation is about the PDF of n starting from a certain phi. So you see, it looks very much like this one, but there are two completely different objects. This one is you start from a certain value of phi, you wait until time equals n, and you look at the PDF of phi. And this one is you start from a certain value of phi, and then you count how many e-folds you need to terminate inflation, and this is a PDF of the time, of the duration. But although they are different objects, they obey almost the same equation. It's only that here you have the adjoint operator instead of the operator, but it's still an explicit equation. So in summary, what you have to do is the following. You take this equation, you solve it, you have the PDF of the duration for inflation, it gives you the PDF for zeta, you integrate it above a certain threshold, and then you have the mass fraction of the black hole. So what I will do now is just to apply this program to a simple example. Of course, there are many more complicated situations you can be interested in with many interesting physical effects, but I just took this simple example just to show a few main results. So here I'm considering a single field potential, which is given by just a constant piece plus a piece which goes like phi to the p. So V equals V naught times 1 plus phi to the p. It's a plot of the potential. And before showing you the result for the PDF of zeta, I just do a first calculation, which is the power spectrum of zeta. So here you have the power spectrum of zeta as a function of the field value at which the mode that you consider crosses out the Hubble radius. The black line, which you cannot really see because it's hidden by other lines, but it's this line here, is the full result in the stochastic theory. So it's the complicated integral that I showed before. And then the blue line, this one, is the classical result. So it's the power spectrum you would obtain by just solving the usual Mukhanov-Sasaki equation for cosmological perturbations. So without taking into account stochastic effects. And what you see that there is a region here where the two agree very well. So it is in fact the region where the saddle point approximation can be made, so where my classicality criterion is satisfied at large field. And then when you go down the potential, the first derivative of the potential becomes very small. So this becomes very small here. It means that the classical criterion stops to be valid. And the actual result is completely different from what you would expect from just solving the Mukhanov-Sasaki equation. And in particular, you see that you vastly overestimate the power spectrum in the usual result. Here it's much smaller. So this is the blue line, and the point at which you transit between one regime to the other regime is exactly given by the point at which this classicality condition starts to be fulfilled. And then the red line here is something different. So the red line is, because you know where the classicality condition is satisfied, you can define a region in your potential which is dominated by stochastic effects. So we call it a quantum well. And then you can approximate or assume that across this region the potential is exactly flat. And if you do that, the result you obtain for the power spectrum is this red line, which you see gives a very good fit to the asymptotics of the full result. So in summary, what we find is the following. If I give you a potential for inflation, you just compute this classicality criterion. If it is satisfied, then you can use the usual result, at least for the power spectrum. For the black holes, it will be different, but at the level of the power spectrum, it works. And in the regions and in the other regions, you can just assume that they are completely flat and trust the result you obtain for the power spectrum. So now I'm going to discuss the probability distribution of n in these two regions, the classical one and the quantum one. So in the classical region, this is what we obtain. So it's the distribution function of n, which is just rescaled by v naught. Different colors correspond to different points in this classical domain. You also have some black lines on this plot. So the dashed line is the leading order of the classical approximation. The dotted line is the next to leading order. So the dashed line is a Gaussian fit, if you want. And the dotted line includes some non-Gaussianities at the level of FNL. Just includes an FNL parameter. So you see that indeed the distributions are almost Gaussian. But in fact, here I'm cheating a little bit because I'm only showing you the part of the distribution which is close to the maximum. And close to the maximum, it is indeed Gaussian. But you will see a bit later on, maybe in 5 minutes, that far on the tail, it's completely non-Gaussian. And even though classically you can succeed in describing the power spectrum, so the neighborhood of the maximum of the distribution with a Gaussian approximation, the tail will be completely non-Gaussian, and you will have to use other techniques. And I will give some ideas of what we could do in this case. In the other regime, in fact, things are easier. Since you can assume the potential to be almost flat here, it turns out that you can solve the problem entirely analytically. So the PDF, here I'm showing the PDF again for the number of e-folds as a function of the number of e-folds. Different curves correspond to different points in this quantum well. So the red one, this one, corresponds to starting very close to the right-hand side of the quantum well. And as you go closer and closer to the left-hand side, inflation terminates here. You have curves which are bluer and bluer and more peaked. So just two remarks about this plot. The first one is that, in fact, it turns out that this profile is universal and only depends on this mu squared parameter. So P of n over mu squared is a universal function, which is an analytical function. And mu squared is just the width of your quantum well squared divided by the height in Planck units. So things only depend on that parameter. And as I will also show later in more details, this function is far from being a Gaussian. So when people use the usual results to estimate the abundance of PBHs produced in flat or almost flat regions of the potential, not only they make errors in calculating the power spectrum, but also because they typically also assume the PDF to be Gaussian, there is another mistake here. So, sorry, because everything depends only on mu squared, I can now take my threshold value and integrate the PDF above my threshold. And then I obtain a mass fraction. So this is the mass fraction you obtain as a function of mu squared. It only depends on mu squared. Of course, it also depends on what is the value of phi at which the mode crosses out the Hubble radius during inflation. But you see that there is not much difference. So the blue curve is what happens if you start very close to the right-hand side. The green curve is what happens if you start very close to the left-hand side. But the two curves are quite similar. Another thing that I would like to stress is that the result is highly sensitive on mu squared. So I don't know if you can see all well, but on the horizontal axis, mu squared only varies by 2 orders of magnitude, between 10 to the minus 1 and 10. On the vertical axis, beta varies between 10 to the minus 60 and 1. So over 60 orders of magnitude. So it is extremely sensitive. Here I've put 10 to the minus 8, the value that I was mentioning before. For some masses, the constraint is even much stronger, so 10 to the minus 20. But you see that in terms of translating these constraints into bounds on mu squared, this doesn't have a large effect, because in the end what you find is basically that mu squared should be much less than 1, or less than 1, if you don't want to overproduce primordial black holes. So this is one important result of this analysis. If you want to remember it in terms of maybe a slightly more physical concept, because everything depends only on mu squared in this case, you can show that the mean number of e-folds it takes to cross this quantum well is also of order mu squared. So what this plot is telling you is that if I give you a potential for inflation, again, you compute your classical criterion, you identify the regions which are dominated by stochastic diffusion. So you know the width of these regions, you know the height of these regions, you compute your mu squared parameter, which is given by this formula. If it is more than 1 or of order 1, then it is excluded because you overproduce primordial black holes. And then if it's less than 1, you need to look at the details. Okay, so this was for the quantum-dominated part. And then the very last point I would like to make is just to flash some preliminary results we have regarding the other part, so the classical part. So here I've displayed again the PDF of zeta in the stochastic regime. The only thing that I've changed is that I plot zeta directly. So it's not n, but it's the fluctuation in n. So it's n minus the mean value of n. And also in the vertical axis, I use a logarithmic scale just to stress that for large values of zeta, you see that it goes to a straight line, which means that the PDF decays exponentially with zeta and not like a Gaussian. So we have exponential tails. And in fact, what I will try to convince you is that in the classical regime as well, we have exponential tails and not Gaussian tails. And we can compute what they are. So the way to do that, or the way to see how it happens and how we can study this problem, is to introduce what is called the characteristic function, which you see is something which is related to my PDF. It's like a Fourier transform of my PDF, if you wish. So I take my PDF, I times exponential itn, where t is just it's like a Fourier mode, if you want. And then I obtain a function of t. And the reason why it's convenient to work with that is that you can derive an differential equation for chi, which is similar to the differential equation we had for p, of course. But the big difference here is that the differential equation we had for p was a partial differential equation, because it was dp over dn is some derivative of phi acting on p. So we had two variables, n and phi. Now we only have one variable, which is phi. So this is an ordinary differential equation. And because it's an ordinary differential equation, in some cases we can solve it analytically. So the idea is that you solve this equation analytically, and then you do some inverse Fourier transformation to go back of the PDF. This is, by the way, exactly how I produced the plots of the previous slides. In fact, what I solved was the differential equation for the characteristic function, and then I Fourier transformed. So you need to do that. So once you have worked out your characteristic function, you need to do this integration. And in fact, it turns out that it's convenient to write this. So you integrate over t. And it's convenient to think of t now as a complex variable. And to notice that typically chi will have poles which are located on this axis with certain values that you can compute, which we call lambda, lambda naught, lambda 1, etc. So when you close your integration contour, you see that because of the residue theorem, you can write this integral as being a sum of the residues times exponential minus lambda n. And the reason, so it's just a rewriting of the solution, but the reason why this rewriting is useful is because this becomes a good expansion along the tail. Because if I only keep the term lambda naught, for instance, if lambda 1 is larger than lambda naught, for large values of n, the lambda 1 term will be suppressed, the lambda 2 term will be even more suppressed, so on and so forth. So if I compute only the few first eigenvalues here, I have a good expansion on the tail of the distribution. That will not work well for the maximum of the distribution. I would have to include really all the eigenvalues. But since I'm interested in the tail, this works well. And in practice, these eigenvalues lambda, they can be computed. So for instance, in the case of the flat potential, the one that I showed before, so of course here I don't learn anything because I already knew how to solve things analytically, but still I can do it. And what I find is that the eigenvalues are given by this expression, and they depend only on mu because, like I said before, there is a single parameter which is mu. But then you can play and change a little bit. So for instance, you can consider a quantum well which has some slope, introduce a slope alpha. And then what you find for the lambda n's is that you have exactly the same spectrum of values, of discrete values as before, but everything is shifted by a constant, and this constant is typically large. So alpha can be small, of course, but remember that V0 is very, very small. It has to be smaller than 10 to the minus 10. So unless you really take a value of alpha, which is very, very, very small, you shift all the eigenvalues by a large number. And this is interesting because it means that, so large value of lambda means a suppressed tail, because it goes like exponential minus lambda n. So it means that as soon as you introduce even a very, very small slope, you will typically suppress a lot the abundance of black holes if you have a constant slope. Now, another case of interest is if you have an inflection point. So instead of introducing alpha phi, I introduce alpha phi cube. And then I obtain a result which starts to look different for the lambdas, which is that they are typically of order the cubic square root of V0 alpha. And this is a very small number, because V0 is very small, and also alpha has to be small. And small value of lambda means a small suppression of the tail, so a very large number of primordial black holes. So it means that if you have an inflection point in your potential, then you, contrary to that case, you expect a large number of black holes to be produced, because the tail is going to be unsuppressed. Okay, so I just stop here and give you a brief summary of what I've talked about. So primordial black holes can be seeded by large density fluctuations during inflation that arise because of quantum vacuum fluctuations. When this happens, quantum diffusion, which here is maybe a fancy word, but just to say the back reaction of the vacuum quantum fluctuations on the background dynamics, when they get amplified and stretched beyond the Hubble scale, this effect plays an important role. Regions of the potential dominated by stochastic diffusion can be easily identified because you have this criterion. Sometimes people mistake this criterion for another criterion for the experts in the room, which has to do with eternal inflation. This is completely different. It's not even the same criterion. If you are in stochastic dominated regions, what we have found is that the system must spend less than one E-fold for PBHs to form. So basically, either you spend more than one E-fold and it's completely ruled out, but if you spend much less than one E-fold, the abundance of black holes is very strongly suppressed. So there is maybe a small region where there could be a substantial amount, but this is a very clean situation in a sense. However, in classically dominated regions, the situation is a little bit different. The standard calculations may fail. So, of course, they succeed in estimating the power spectrum, but because they don't succeed in describing the non-Gaussian tails, we might have to use the stochastic delta and formalism to improve our understanding of what's happening there. And then, of course, here I've only discussed the simplest case where you have a single field, but in multiple fields this could be studied as well. I've also restricted myself to the Thoreau approximation in what I've showed, but we could go also beyond these approximations, and there are some subtleties. But this is work in progress. Thank you for your attention.
Thank you for the nice talk. So are there questions or comments? Yes.
If the black holes form through inflation, they will be diluted. I mean, how do you cope with the survival fraction of inflation?
Yeah, so they don't form during inflation, but what forms during inflation is the curvature fluctuation, which goes on large distances, and then it does nothing until it re-enters the horizon. But when it re-enters the horizon, inflation is over. So then it becomes the usual, it becomes like in the standard, it gets diluted because of the expansion, but in fact, because they behave as pressureless matter, in the radiation era, the contribution even increases, and then in the matter era, it just freezes. But there is no extra dilution due to inflation.
Another question or comment? Yes?
So maybe you can take me through what happens in the trivial case where you have a constant potential,
Yeah.
which would amount to just having inflation never ends, and you have an infinite width of the potential.
Yeah.
In the formula description, it seems to me like that you would imply that you get an incredible amount of black hole effect.
If you have an infinite width, then yeah, because then mu becomes infinite, and so yes, that's right.
But that doesn't square with what I'm talking to you about consider expansion. You're saying consider universe will always
No, because if you really have exact, the thing is, if you really have infinite de Sitter, I mean exact de Sitter, then what this is telling you is that you produce, okay, large curvature fluctuations on large scales, but because these scales, they never re-enter the horizon, they never recollapse into the form of black holes. So if you want the scales to re-enter the horizon, you need inflation to terminate. And if it terminates, it means that your quantum world is at least bounded on one side. No, so in this model, I assume that, sorry, I should have said that, I assume that when phi equals 0 here, inflation terminates. So either there is like, the potential becomes suddenly very stiff, or maybe it's coupled to another field and there is tachyonic instability or something like that happens. Yes, that's right. I need another mechanism to terminate inflation. The constraint I showed on the BBH as dark matter, no, it's just based on, so I'm not an expert, but yeah, this plot, right? Yeah, so they have different origins. For instance, this one, so femtolensing, macho, Eros, these are micro-lensing constraints. So, for instance, femtolensing, I think, comes from Fermi, and it's just so from the micro-lensing of GRBs. So basically, if you have many PBHs in the universe, you expect them to do some micro-lensing events. And because you don't see them in the data, you can exclude that they are too abundant. This one here, so the gamma background is for very light PBHs. So if the PBHs are formed with a very small mass, they would emit Hawking. So every black hole emits Hawking radiation, but these ones, they would Hawking evaporate. And that would add a contribution to the gamma ray background that we don't see. So we can exclude some region. And then there are some other stuff like this one, which is the neutron star capture, which is the fact that if we have many PBHs, they should absorb neutron stars by merging. But because we see neutron stars in the galaxies, and it puts some limits. But in fact, this is very much debated because it depends a lot on things which are difficult to model. There are also constraints from the CMB. So these ones, and you see these ones, they concern very heavy black holes. And they come from the fact that if you have a very heavy black hole, mass should accrete on that black hole. And when it accretes, in the accretion mechanism, it heats up, so it releases light. And this light can ionize hydrogen. So at some point, people thought that we could have constraints from the spectral distortions of the CMB, but in fact, it turns out that no. I mean, in the end, there are some constraints, but they are not competitive. But because it changes the recombination history, you still have changes in the CMB, so you have some constraints here. So they have different origins and levels of confidence as well. Yeah.
Does that depend on whether you are working at slow or also
The threshold for the potential or for zeta C? Yeah, so this quantity is, of course, it's not as simple as that, because in practice you amplify many Fourier modes, and then you have a scalar field with some inhomogeneities, which has some profile in real space. It can be asymmetric, it can be complicated, and starting from this profile, you can see whether or not it forms a black hole. But it's not only just the value of zeta at what single scale. So now what you can do is imagine toy models in which you only peak at one scale. So you have a inhomogeneity at a given scale, spherically symmetric, for instance, and see whether it evolves and forms a black hole. And then you find some value which is of, I think the actual value now is 0.086 or something like that. But it depends a little bit on how you model things. But in reality, again, it will be a bit more complicated. It's